Well, good morning and welcome to today's Ascendo Reliability webinar. And today we're going to talk about another facet of accelerated life testing. And really the first step is figuring out how to plan one and sort one out once you've decided that we really need to know how long this widget's going to last in some particular environment or component or system or whatever. So one of the key things, and I'm sure you've heard me talk about it, is, and if you've ever asked me a question related to accelerated testing, uh, I will always ask, well, what's the failure mechanism? What is it that is it chemically based? Is it mechanically based? Is it wear? Is it corrosion? Is it, what is the underlying phenomena that's leading to failure that you're interested in quantifying? It's time to failure. And well, that's the purpose of an accelerated life test, is to uh, map out the time to failure distribution or some information about time to failure for some type of failure. And knowing the failure mechanism is a key first step, and something you really do need to know. The other part of this is that we often start early on in our accelerated ALT planning by looking for a model. It makes planning a whole lot easier if we already have a relationship between the testing stress, the increased stress, accelerated stresses, and the translation to use conditions. Now, sometimes we don't have one of those that's already well known or well used or certified or whatever we want to call it. And we'll have to create an acceleration model. Now, that's just one of the key features we're going to need to talk about. But another one, and I've talked about this on some of the previous webinars on this ALT, is we have time constraints and resource constraints and testing facilities constraints and um, knowledge constraints, you name it. We've got limitations. And generally, not always, but generally, we don't have enough samples. We don't have enough time or funding or whatever. There's always something. So keeping those in mind and getting a good handle on what those are is a great place to start as we go down this path of setting up an accelerated test. Now, let's say we've got a new widget. It's a switch, and it's a new technology. It's a new way of doing power on, power off, for example. And we get asked as part of the development team, um, well, how many times will this thing work? Right? We're selling this and it's going into a home or a small business application. And we want to make sure it'll last at least the warranty period and hopefully a lot longer. Our competition is the standard switches you see on the wall that turn on and off the lights, for example. We want to replace that with something a little cooler, and we think we can sell a zillion of them. Oh, and by the way, um, we want it to be, confident that we have a good switch and that it lasts long enough, and on and on and on. All right, so let's play with this idea for a moment, and let's think about what are some of the things we need to know if we're going to design an accelerated life test for this new light switch. All right, so hopefully you immediately thought about, well, what do we know and don't know? What is it? We don't come into this question completely absent of all information, although the way I just presented this, you've got very little to go on except it's new. So let's take a closer look at this. Now, the first step is I outlined right at the start of this presentation, and anytime I talk about accelerated testing, well, what's the failure mechanism or maybe mechanisms? right? So if this product's been in development or it's at some stage, maybe our design engineers, mechanical, industrial, or software, or whatever team that we have available that's working on this, they may have a pretty good idea of, well, this is how it fails. What did we learn in the early prototypes? What were the types of failures that occurred there? Are they just delayed because of the design improvements, or were they eliminated? And then also, how does the known failure mechanisms, and not just one, but all that we know about, how do they respond to stress? So it's funny how different mechanisms will respond to increase, say, pressure or temperature in completely different ways. Some will respond to it benignly and not really care one way or the other what the temperature is, and others will just exponentially increase their rate of failure or fail much, much sooner. But it depends on that interplay between stresses, because the one that we are interested uh, in, because it's the one that dominates at use conditions, it may get swamped or hidden because some other mechanism starts to appear at higher rates with an increase in a particular stress. So I'm being kind of vague here, but let's say our switch is got a mechanical part and a software piece to it. Now we're interested in will the software element of this um, survive, say, 20,000 actuations. And now you could argue that, well, it's software, it won't wear out, it won't do this or that, the other thing. Yet we haven't really evaluated the software yet. And so we're looking for other bugs and different circumstances to do it. But we also are curious about the mechanical element that basically breaks and connects the connection, and the spring that's involved with that. So we know that the spring at normal conditions will last, a long, long time. But if we increase the temperature, we know that the way that spring loses its ability to activate the switch um, decreases. And we have an understanding that temperature will accelerate it. Now, the software part, which we may be more interested in, doesn't really change at all with temperature that we know of, because it could be an interaction with the change in conductivity of copper, for example, and timing and things like that. But it's the two different failure mechanisms. One may mask the other one if we don't pay attention that to the ones that we're interested in. So just because we can increase the temperature, it doesn't really matter with the software. So that may not be a good stress to increase, because it will increase something we know is going to fail due to increasing temperature. And so let's not go there. So that's one example. Understanding the failure mechanisms, whether it's metal fatigue or a timing issue or memory banks getting filled up, or some element that gets consumed with each thing, arcing across the contacts, a deterioration or melting of components, poor manufacturing, uh, all of those different kinds of mechanisms and symptoms can help us suss out, well, what are the related stresses that we should or should not apply in order to get a clean picture of the mechanisms we're most interested in. So that's if you take nothing else away from this discussion, it's pay attention to the mechanisms. Now, if we have an existing model and we know it really well, and it's the solder joint fatigue due to cracking through thermal cycling, then let's get the Norris-Landsberg equation out and let's use that. And there are a handful of other models depending on your particular circumstance. But there's a caveat there. Does it apply in your particular circumstance, right? Just because it works with sack solder, does it work with your very low temperature solder or with the technique that you're using? Is the existing models or our understanding of the relationship between stresses and use conditions, does that apply in your set of materials, design, and use environments? And the further away you get from using a model that truly works for your situation, the more of a random number that you're going to get out of the process. There are models out there. There are physics of failure models out there. There's models in literature. Um, each one of them may provide a way to do an accelerated life test and do that acceleration factor calculation for you. But in others, it's just not going to be useful for you. It's just going to create a random or a misleading result. So as you look for models, be very suspect as to whether they're useful for you or not. Now, the other thing is something that we may know or not know is, did we do prototypes? Did we build some systems up? Even breadboards, early builds of our particular device, this particular switch. Well, what did we learn from them? What are the things that worked or didn't work? What were things that we know from experience and from our engineering team and management team and inventors? What do they know? What do they know about this material set or this vendor or this particular device or construct of a design or manufacturing process? Now, some of this can be captured in an FMEA. Let's go through that and understand what are the potential failure modes, right? And then for the dominant ones, let's figure out, well, what's the underlying mechanisms for those things. Now, sometimes our history will lead us astray and saying, oh, we've been building these for years, but we're just going one more amp higher power. Well, is there enough margin there? Or do we have something that's changed just a little bit too much to be useful anymore? And so between looking at what's the failure mechanisms, which ones do we know and don't know, what's the models and history that we have, allows us then to frame a good starting point to plan your accelerated test. All right, so let's narrow this down a little bit, and let's say our example here is a metal fatigue. We have this fancy new spring that enables the switch to stay open or to stay closed, depending on which way it's activated. And we found in early on testing that there was a metal fatigue in this metal bending. And so there's been a couple of steps to figure out how to mitigate that and push it out further. But the question remains, will it last 10 years, for example? What proportion will fail in 10 years? So let's say it's a metal fatigue. We've got this fancy alloy we're using. We don't have a really good model or information about it. And that's what we know. So all of our research and everything else got us this far. Now, of course, there's all kinds of considerations that now start to come together to allow us to create a accelerated test plan. So one of them is, well, how much does this thing cost? And how close can I get to the actual finished product? Or what kind of trade-offs am I making in the prototype process? So if I'm doing 3D printed prototypes, but I'm going to do a molded part for the final, are they close enough in their performance and transference of stresses, for example? And also, how much is it going to cost to apply stresses to this product? If we're going to use temperature or current or cycling of the pressing it on and off, how are we actually going to do that? Now, in one test I worked on years ago, was an arm that allowed you to take this camera head basically and position it in a position and it would stay there. And you could move it over a pretty wide range of motion. And the idea was that it was balanced and just the right stiffness that allowed a person to easily move it. But once it got to a location, it would hold still. And so one of the concerns was is that repeatedly moving this thing would degrade some of the couplings and some of the structures that held the in place, and so it would drift or it would fail altogether, and then this large camera head would fall. And so one idea was to create a robot, basically, or just a device that would mechanically move it through its paces, through its different range of motion, all the way up to the right, all the way up to the left, on the bottom, in the middle, up and down, left and right. And that was going to be very expensive. And it was pretty much, it could go, if you were 6 feet tall, it could go as high as your arms could reach. So it could get pretty high, and it moved left and right, quite a bit. It moved, say, 6 to 10 feet, depending on which particular angle you're moving. So it's a pretty good sized device. And a robot to control that, or a mechanical structure to control that and repeat that motion, would be a whole development project in and of itself. And so this team decided to hire a couple of athletic minded interns, and they did workouts on a regular basis with this thing until they got to the number of cycles that they were interested in. It was easier to program a couple of interns than it was to create a mechanical system to do the work. So that was part of the cost of applying the stress. Now, sometimes it's vibration or a thermal chamber or a thermal humidity chamber or something like that. Those all have costs. Now, the other part of this is, what is it going to take to make the measurement? And so for our little switch, we're looking for metal fatigue. Now, do we need to destroy the device to see if there's fatigue there? Or is there a way to measure the loss of the spring's capability with, say, a force measurement? How precise do we need to be? In each of those types of considerations of destructive testing means we're going to need more samples. Or if it's a precise measurement system, do we have that capability? Can we actually perform that measurement accurately enough and without a lot of measurement error? And do we have all of the other elements, the resources necessary to just conduct the test? Or do we need to rent some equipment or buy some equipment or work with a laboratory nearby or whatever? But it's part of the process as you start narrowing in on a plan, is consider, well, what can you afford and what can you not afford? And what equipment do you have and what resources and techniques are readily available and which are not? Now, back on measurements, you got to think through, what exactly are you measuring? And I believe on one of the earlier webinars, we talked about that sometimes you can measure something where it's very clear. It either passes or it fails. So if we flip the switch and nothing happens, it's open and it stays open after we activate it, or it's closed and it stays closed after we activate it. Well, how exactly are we going to measure that? Right? If the mechanism is hidden within the body of it, we may not be able to see it. Or is it something you can obviously feel? Or could we put a small current through there and just look for it to change state, to go from current flow to no current flow? Maybe put a small light on it so that we could see if it turns on or off or changes. But how exactly are you going to measure it? And is it measuring what you're interested in? Right? If I'm interested in when the metal fatigue starts, will that change the resistivity of that contact enough that we can actually measure it? Or will it change the spring force such that we could measure that? Right? But if I'm looking for it to be just not working at all and not just the onset of metal fatigue, that may change the nature of how we make the measurement. But is that really what we're interested in? So think that through very, very carefully. Because once we know it starts to crack and propagate a metal fatigue crack through the metal, it's just a matter of short time before it fails. So we may be interested when that occurs, and then how many cycles it takes to cause failures, a two-step process. And then it might be a variables type data, right? Number of cycles to failure. But if we go to the number of cycles to it just fails, well, we could work with that as variables data, or we could say, oh, it has to do 10,000 cycles and it's pass fail at that point. That's an attribute data. So depending on what we're measuring and what we're interested in, it may change the nature of the data we're collecting and how many samples we're going to need and the cost of measurement and all those other parts that come into it. All right, now there's could be all kinds of other mechanisms out there. What if our prototype has some contamination in it that levers that spring so that it sees more force than it would if that contamination wasn't there? What are we going to do then? Right? If we run the test to failure, we open it up to make sure the failure mechanism was the one we're interested in. The metal fatigue looks exactly like we would expect it to, yet we find this random piece of wire in an interesting place. Right? Is that enough to change the nature of the failure mechanism? Or what if we open it up and it was a shear, overstressed total shear and not a crack propagation type failure? Completely different mechanism. Or what if the polymer housing deformed before the metal fatigued at all? So as we get failures in the test, or as we consider the types of failures we're looking for, how can we tell the difference of what's causing the problems? And how do we, this is the part to think through, is how are you going to confirm the failures you're getting actually are ones that you're interested in? And two is maybe it's a chance to learn something about how your product is going to fail. Right. So we done some more considerations, thought through a couple more things, and now we start to ask questions about, well, how often will this switch be used? And so after a handful of meetings and a bunch of studies and all this other research that others have done, they come up with the specification is that they expect 2 cycles a day, but they would say it'd be very unusual to have more than 20 cycles per day. So there's an option here. You could run your test such that it's just 2 cycles per day. Or you could say, well, let's test for the worst case. Now, obviously there's a distribution, right? Some installations will rarely, if ever, be used. Some will be used to some extent. And they're saying on average, or the median value would be 2 cycles per day. Or I should say the mean value is 2 cycles per day. But then, yeah, it could be as high as 20. And let's say that's 95% percentile is 20 cycles per day. So 5% of the population would use it this frequently. So we could, balance out our duration of the test, how many cycles we're going to run based on, well, what proportion of the population are we testing for? So if we shift down to say 80 percentile of the total expected usage differences across the population, instead of 95 percentile at 20 cycles per day, we might be at 10 cycles a day and cover 80% of the population. Now, depending on how good your data is, this may or may not be as useful. But oftentimes, if everything else allows, is we usually go out to the worst case or the most frequent use or the highest temperatures or things like that. It gives us a little bit of margin in the testing in order to say, well, if we're testing it at 20 cycles per day and it's not exactly right, and it only covers 90% of the population, well, that's still 90% of the population that we've got some information for, as opposed to going at a lower value or a medium value where we would learn nothing about how this product works out on the tails. And so I'm not sure that makes a lot of sense, but the idea is we often pad our uh, the design of the reliability test out to worst cases or a high percentile of use, such that if there's errors, it errs in a conservative way. It allows us still to make reasonable conclusions for the bulk of the application's expected stresses. So hopefully that makes sense. All right. Yet another thing to consider is something you've heard me say a number of times in previous webinars and discussions is everything varies, right? And part of drawing a sample from a population that we haven't even built yet is that we want enough samples to account for the range of variability that we would see. And sometimes that's making the assumption that our sample is randomly selected such that it represents the variability of the larger population. Now, in a product development stage, where we haven't gone to production yet, we don't have the whole population to draw a random sample from. So we're going to break that assumption pretty quick, but it's still something to consider. Now, one of the ways that we get variability is measurement error. And so it is a good step to, after you've honed in on what it is exactly you're going to measure, it was make sure that your measurement error from that process is sufficiently low that you're not just adding a random number to your data analysis. All right. And by that, I mean, do a measurement system analysis assessment. And even if it's just a gauge R&R, and make sure that your measurement error is less than 10% of the specification that you're measuring against, right? Now, this is a whole topic in and of itself, and hopefully you're familiar with MSA to some extent. If not, there's plenty of other resources out there, and it might actually be a good topic for another webinar. But not checking it, especially when you're being creative about how or what you're measuring, is a good way to really muddy up your data such that it becomes meaningless to you. So do the due diligence and make sure your measurement system is adequate for the task you're asking. Next is, well, everything varies. So the materials, the mold, the metals, the types of use, the pressure used on the switch, the angle of attack on the switch, all of those things vary. And the more of that variability we can account for in the sample and in the test process, the better. The idea is that if you set up a very simple pneumatic device that flips the switch from one state to the next, and it always hits it at the same angle with the same pressure, and uh, everything's the same every single time, we're missing out on the impact of, say, fingernails that do a force concentration, or of a hitting the side of the switch, or hitting it harder or softer. Each of those types of variations may lead to different kinds of failure mechanisms becoming dominant. So if we make one type of switch and it just repeats it over and over again, if that's evoking the dominant failure mechanism we're interested in, well, you might get away with it. But I've also seen it where in a test where it was mechanically done, and but it didn't represent, and it was just a straight line hits the switch basically. Whereas if a person did it, and this was a switch for a medical device that had a polymer coating over it to keep the cleaning agents out of the electronics, is that fingernails in the end of a pen, um, did enough force concentration that it would poke through that membrane, and then contaminants would get in, or cleaning solutions would get in and destroy the mechanism of the switch. And so by not considering the range of variability of how people actually would use the device, we miss some very important variables in setting up the test. Now, if you can include the range of variability, now that adds another complication to test planning, yet think it through. Do you have all of the different types of variability thought through, and which ones are you going to use and which ones are you going to control, and be clear about that and make sure you think that through very carefully. The other part of this is that if we're doing time to failure testing, for example, we're measuring the number of cycles until we get a failure, and we want to do, say, a Weibull plot off of that, we're going to be essentially fitting a curve to our data, and it's regression analysis. And so the less noise in the system, the less measurement error and process variability, which is in the measurement system itself, which goes into measurement error, but also the amount of variability in the materials itself that we can control will help us to get a cleaner fit. But it's at a trade-off. That's more expensive, and it doesn't reflect the natural occurring variability. So again, it's one of these steps that we need to think through very clearly, that the noisier the data, the harder it is for us to do the regression analysis and get a meaningful result. So it's something to be very careful about. So what else should we consider? Now, since I'm recording this without the live audience after 2 tries, I'll leave this as a rhetorical question, but what else should you consider? I'm sure I haven't covered everything, and we could talk about this maybe when we do our Q&A session. All right, let's go back to our simple example. We got this little switch, right? And so we figure out, with the help of marketing, some of the field research, and kind of the application it's expected to be in, that we're going to use the 20 cycles per day, and we're going to say we want it to last 10 years. And, well, let's see, I mean, it's 20 times 365.4 times 20 or 10, whatever, 10 years. So 10 times 365 is 3,670. Let's round that up to 4,000 times 20 is what, 80,000 cycles? Is that right? I'm doing the math in my head very fast here and out loud, which is probably silly. But anyway, we can calculate that we expect it to have to survive, let's use 80,000 cycles. So we could create a system or hire interns if we really wanted to, but we could probably find a system that would flip this switch that many times in a reasonable amount of time. Now, one of those extra considerations is, well, if we do it too fast, what's going to happen? Well, it's going to heat up, and that may really alter its performance. So we want to make sure that the rate that we do the automation doesn't induce other failure mechanisms, other stresses. So anyway, so we figure out that we need 80,000 cycles, and that's represents a lifetime of our product. And so at that point, if we don't want to run out to failure, we want to have the minimum number of samples that we can have. We can use a C equals 0, or what I call a success test. And that involves the confidence, the C in this equation, M is the number of lifetimes. So if we run for one switch for one lifetime, that's 80,000 cycles by my quick random calculations there. And we want to be able to demonstrate with that confidence that we have at least, say, a 90% reliability. And so I use 90% confidence, 90% reliability because I know the answer to this. It's 22. All right. So if I put in 22 samples and they get actuated for a lifetime or 80,000 cycles each, and they all pass, then I can say with 90% confidence that our population should have at least 90% reliability to that set of conditions, that lifetime. Now, the acceleration we're doing is just flipping the switch more often than it would be during a normal day. So the duration of the test is contingent on, well, how fast can we flip this switch and it not heat up or cause other problems? And so we might set up a system that does it, say, 20 times an hour. And so 20 times an hour, we can calculate then how long does it take to get to 80,000. You might be able to go faster, but it'd be cautious about how fast you go because it may induce other types of problems. So anyway, we can quickly design a test, and it's not the most elegant test, right? We're just saying it's a attribute data. It's pass fail after so many cycles. Now, a downside of this simple example is we're using a simple model that says we expect the switch to be used no more than, say, 20 times per day, and we're going to do it 20 times per hour, and so we can do a straight line translation. So if it runs 80,000 without failing, that's equivalent to the 10 years that we expect it to do in normal conditions. I just thought of another caveat to think of. When we do this fast in the lab, there's not time for dust and humidity and all these other daily factors that come into play, UV exposure and so on, to degrade the materials. There's just not time for that to occur. And so you might want to think about that also. Does those kinds of stresses impact our calculations? So now if we get, as I mentioned earlier, I'm going to see if I can get a pen going here. I can do that. I can do that. And hopefully this will show up. So let's say I have my 10th percentile of failures, right? 90% reliable. And I go out to some point in time. And this is my 80K cycles, which is our surrogate for time. It's cycles. All I know is I have 1 point. 80,000 cycles, it's better than 10% defect rate. It's survived 10% of its the 10th percentile of failures hasn't occurred yet. So we suspect we're going to get failure some point off of this, but we don't know if it's going to be very steep or very shallow. We don't have any other points in order to draw out what's going to happen here. And so all it's giving us, if we've had no failures, it just says we're 90% confident of 90% reliability, and that's it. We don't know what it's going to do after 80,000 cycles. So it's a very simple example, but it's also a very common technique when you can cycle something faster or use it faster than normal time. And it makes it very easy. And also you don't have to go to failures. And other part of this is that it being simple is we're giving up having failures to make sure that the stresses we're applying actually produce the failures of that metal fatigue that we're interested in. And so simple sometimes means a lot of trade-offs and lack of information, but it makes it simple. So what else can we do? What's another way we can go about doing this? Let's see if I can get rid of because I know that my annotations will show up on the next slide. So let me do this. Get rid of that. Go to the next slide. Now, if we're not really happy with just a simple test and we don't have a good model, right? Well, let's say we're going to use different pressures, different amount of force that's being applied to the switch as a way to accelerate the failure mechanism of metal fatigue. And a dome switch is, well, not really, because it's a pretty heavy spring. Anyway, we'll use it hypothetically, a different example. So in this case, we're going to use 3 different sets of stresses. Say a moderate, a high, and a very high load, and then cycle our tests. And then we're going to create a model off of that in order to translate our loading to our use conditions. And we go about often measure a bunch of people, how much force they apply when they're pushing this kind of switch. And we do some research and find what's the range of the ability of a person to push on something, those kind of things. And we can do some interesting stuff to quantify what's the expected load that this product is going to see. And then the mechanical engineers figure it can go up to a very high load without shearing or fracturing in all kinds of ugly ways, but we can get all the way out there. All right. So at the end of the day, we end up with 3 different stresses. Let's see if my pen's working here. Yep. So I have my very high stress and high stress and medium stress. And if we're lucky, they kind of line up on a relatively straight line. And it allows us then to extrapolate out to use conditions. And then we can read off, the number of cycles we expect this to survive. Now, if we run to failures, then we can get a distribution. And I'm drawing them purposely skewed because it's probably going to be something other than a normal distribution. And then we can run this whole extrapolation down here. And as this thing crosses the line of the use conditions, it's going to create a curve. And so we can pick off when the first percentile is, when the median values are, when all of them will fail, and so on. And it allows us to get a way more information, yet we need 3 different stresses with enough failures that we can fit a distribution. Now, of course, you could do 3 different stress levels and just do the 0 failures type models, but it really adds another whole level of risk to counting on those samples and the expense and making a couple of assumptions and a couple more dimensions of assumptions that further erode the ability of this model to work. So if you're going to 3 stress levels, run them to failure. Run enough samples to failure, you can get a reasonable idea of this distribution that you're dealing with. So that's a next step, another step to take it more in complex, but you get a lot more information out of it. So I can tell you from our loads here, if we figure out that our customers are really light-handed, well, we know then we can say our time to failure is, or cycles to failure is longer, and vice versa. It gives us way more information and allows us more resilience in interpreting our results for subtle changes in the conditions as we learn more. So those are all good things. So let's get all this. Someday I'm gonna have to learn the short keys or hot keys or whatever to take care of that. So this ended up being a presentation about how much we need to know in order to do accelerated testing. And that was my intent. And we almost never know enough. And so part of the process and one of the constraints you got to watch for the most is, do you know enough to set up a test? You won't know everything you need to know, because then you wouldn't need to run the test, because you already know how long something will last before it fails. So we have a question to answer. Do we have enough information about the failure mechanism, about the constraints, about the criteria, and how to make the measurements, and minimizing our very unwanted variability and increasing the wanted variability, and so on, such that we can design a suitable test that allows us to get the information we need. And so it's always going to be a balance. It's always going to be a trade-off. And very rarely do any two accelerated tests become identical. It's because the differences of what decisions are need to be made based on the results and the set of constraints and all those kind of things. And so as you work to build an accelerated test, hopefully this gives you a set of tips anyway of what to think about as you go about doing that process. And finally, this has been my third attempt to get this webinar content out. Last month, we had technical problems with my software. This morning, the day I'm recording this, we tried to do the webinar, but our internet went out. So I ended up having to bail on that one, and audio just wasn't going to work. And so here I recorded it on my desk. If all went well, I'll be able to post this shortly, and then we'll set up some time to talk about it. So if in the meantime, let me know if you have any questions. You can find out more about accelerated testing at Accendo Reliability. You can also find how to get in touch with me there too. We always look for questions that we can talk about in webinars and or our podcast. So please feel free to get in touch and watch the newsletter and or messaging to talk about when we're going to set up a Q&A session for this event. And so with all that, thanks so much for attempting twice, and hopefully we'll see you at the Q&A, or we'll just talk separately to make sure you get all your questions answered. So with that, we'll call it a day and hope everything works out. Talk to you later.